So first, I want to invite Maytal Saar Tsechansky from the University of Texas at Austin. And I'm personally very excited. I told you earlier, I read like 10 years ago a paper about active learning in the Machine Learning Journal. So, and as Bracha said, you're a graduate from Ben-Gurion, so it's a pleasure to meet you. Thank you.
Thank you. Yes, so I am a graduate and a very proud one, and I'm delighted to be here and see familiar faces that seem to not change much. So it's good. It's great to be here. So as Robert said, I'm at UT Austin. I'm at the business school there, but I do work in machine learning and data mining. And in fact, I started getting interested in this area and actually developed a lot of my expertise here at Ben-Gurion University. So I owe a lot of what I do now to what I've learned here. This is what I'm going to do is joint work with Tomer Geva and a master's student at Tel Aviv University, or Lustinger. Much of my work, like Robert said, is in the area of information acquisition, active learning, and reinforcement learning. And this piece, in fact, that I'm going to talk about today is very different, in fact, from most of the work that I usually do. It's a little bit more applied and hopefully would be also useful and quite interesting. So just to give you kind of a bit of an introduction, as you know, this audience well know, machine learning is quite integral to a lot of decision making that's being done today, and this is becoming more and more routine in an increasingly number of domains. And data is in fact, as I mentioned earlier, a significant part of my work has been in the area of information acquisition. And the importance of data in the process of learning, or data-driven learning in general. So I like to think about data as the ingredients from which learning algorithms or induction algorithms generate patterns or knowledge. And if you don't have good ingredients, like any good chef knows, then whatever you learn from this data is being undermined. And so that, in general, as a research problem, led me to deal with policies or methods for intelligent information acquisitions. You know, we're in an era of big data, and we always talk about how much data we have and what we're going to do with the data. But the fact is that there are a lot of domains where good data is actually rather sparse, and that includes cases where it's very costly to acquire information. I mean, even if you think about if information is acquired by interacting with customers, these interactions are not necessarily costless, but there are other domains where you have to do some medical tests, et cetera, to acquire information. And so how do you do this intelligently to learn the most out of this data is an important area of research. But obviously, even if you have a large data set, like large hospital medical data sets, a lot of this data, there are a lot of attributes that you could potentially have information on, but if you look at these data sets, a lot of them are missing, or this data is rather sparse. So in this talk in particular, I'm going to focus on cases where it is costly to label, and what I mean by labels are in the context of supervised learning or predictive modeling, is when the dependent variable value is unknown and needs to be acquired to generate or to learn predictive models. So I'm going to talk about cases where labeling instances is actually costly, and this has become a particular issue. Either if you need to acquire a very large number of examples to learn a good enough model that is practically useful, or if we're in a domain where the concept that we're trying to learn drifts over time. And so you constantly need to acquire new training examples, new labels, and you need to make sure your labels are contemporary and reflect the current patterns that you're trying to learn. And if you're in this setup, then you need to start thinking about how you acquire intelligently these labels so that you can learn. And again, the objective is that we want to spend this money on acquiring labels intelligently so we can learn better predictive models at a lower cost. And one sort of recent developments that made these things could be useful towards that are online labor markets, sort of like Amazon Mechanical Turk. And a lot of companies have started using those to label instances that they want to generate predictive models on. So you can think about labeling images or even labeling content. We talked about content analysis, but even labeling content in respect to whether there's some hate language or something in that particular image for advertisement, etc. And the benefit, of course, is the low cost. So there are a lot of people out there who are willing to do these labels for a very small amounts of money, and you do need a lot of labels, but this makes it very feasible economically, but it's also available. So any given time you can put out a job where you have thousands of images to be labeled, and you have hundreds of thousands of people out there who might be willing to bid on these jobs and label them for you. However, research have also established that the quality of the labels that you acquire in these markets vary quite widely. And this interesting thing is that different research found, and what you see here is actually results from different research that other people have done, that showed that for different costs, and what you see here on the x-axis are the costs that you pay for labels, you get different quality of labels. And these different research pieces kind of disagreed on what is the pattern, what's the relationship between the quality that you can get for different costs. And what it turns out is that the reason that these relationships really vary is that they depend on many different things, like the competitive setting, what other jobs are available on the market. But furthermore, because these are global markets, there is mobility in the demographics that become available at any given time. So depending on what time you put your job out, there may be a different population of people who might be looking at it and examining it. And again, as I said before, depending on which other jobs are competing with you as someone who put out these labeling jobs, you'll get different qualities, which is what we see on the y-axis here, different quality for different pays. So that kind of give rise to what I think is actually a new problem that we called adaptive labeling payment. So if we really don't know at any given time, for any given setup, for any given arbitrary task that I came up with that I need labels for, I don't really know what the relationship is between the pay that I can offer and the quality of the labels that I'm going to get. And in fact, I can very well assume that this would change over the course of time in which I'll acquire labels. Then we want to come up with a policy that adaptively prescribe what should I pay, or what pays should I offer to get labels, so that I can get the best, I can learn from this data the best model, the most accurate model at the lowest cost. Okay, so this had to be adaptive because, as I said, these relationships potentially can evolve over time. And in fact, at the outset, you don't really know what you encounter, what sort of relationship you encounter. So wherever you are in a given competitive setting, but even along the learning curve, you want to figure out if I'm going to pay, if I'm going to offer 10 cents per label, is that going to get me to a better place than if I were to offer 50 cents per label, etc. And what we want to get is we want to get a best performance per unit cost that we spend on labeling. So, just to kind of give you a framework, so if you are, say, have a certain training set that you start with, this adaptive learning, adaptive labeling policy will decide how much to pay, and given the prevailing, I don't know to what extent this is visible, given the prevailing relationship in the market between the quality of the labels for any given pay, you'll get labels, and they're never perfect, right? So, but the quality will really vary depending on this relationship. You'll get labels. Some of them will be correct. Some of them will be junk, will be incorrect. You'll add those labels to your training data. You learn a new and updated revision of your model, and then you'll update your policy and say, okay, what's the next best batch to acquire? What should I pay for the next batch? And in that sense, we'll adaptively change what we're offering for these labels to optimize, not to optimize, but to improve the quality for the cost. So the key challenge, the real key challenge in this setting is at any given time, the data that we have available to even decide where we are on the learning curve, you know, how good is my model right now, and what will I benefit, you know, to what extent learning will benefit if I were to go and acquire labels at a particular cost. Everything, all this, is inferred from data that is in itself noisy. That is, the data that's available to us at any given time has been labels with errors, and we don't know which ones are true and which are wrong. So that's the key challenge for this problem. And as I said before, you know, one option would be to potentially to say maybe we can just learn or infer for any given cost what would be the quality itself. But as I said, you know, even depending on where you are on the learning curve, acquiring high quality labels may generate different improvement in your learning than when you are on the lower part of the learning curve. So we fundamentally decided that it would be wiser to just directly try to estimate what is the expected impact on learning if I were to now go and acquire labels at 10 cents, 20 cents, 15 cents, etc. On, you know, using noisy data to make that inference and try to see whether we can reach better models at a lower cost. So the key idea, since I only have really a few minutes left, the key idea was that we used here was to actually remove some data that were acquired at a given cost from our current training data and try to assess, and again, we have noisy data, but try to assess the drop in performance as a result of that. And that would be sort of a proxy, an estimate of the quality or the benefits, the potential benefits of acquiring another batch at the same cost. So by removing a set of instances that we acquire at a given cost and seeing to what extent it undermined, you know, my model, so learning a model with and without his example, it's a very simple idea. That would give us an indication how informative it would be to go and acquire examples at that cost. But as I mentioned earlier, and this is kind of what we're trying to do, we're trying to actually remove, omit some examples that I've already acquired at a given cost and see to what extent it hurts my model. I may have acquired them much earlier, but it will give me a proxy, it will give me an indication of the potential marginal benefits if I were to go again and acquire examples at this cost. So I'm going to skip that, it's just an illustration. Again, the challenge is that all these is nice kind of as an illustration, but the problem is that I don't really know that I'm here on the learning curve because this is kind of will be estimated from noisy data. And when I remove examples and relearn a model, again, it's all these drops in performance. And by the way, it could be even an increase in performance if you omit something that was acquired, some labels that are very, very noisy and very bad. They might have hurt your model. So when you remove them, you realize that actually your performance improves as a result. But the issue is in all these estimations is that all the data that you have is data that is imperfect, that has a lot of noisy labels in them. And so the way we addressed the noisy label problem is that we concluded that this is kind of an estimation variance problem, that we don't have really these errors in labeling or these mistakes in labelings by Turkers, for example, Amazon Mechanical Turk, there's not a consistent bias there, but there's rather, these are kind of random errors or random mistakes. And so our objective was to reduce the variance in our estimation, and we do this in two simple ways. One is that instead of removing all the examples that were acquired, say, at 10 cents and see what the damage is, we remove multiple subsets of examples that were acquired at cost, and average the impact that we measure. And that reduces, again, the variance of our estimation. And also, we repeat these cross-validation estimations multiple times to get a better assessment. So I'm going to, and the last piece is that, of course, we only remove instances that were labeled recently, because, as I said, there could be a drift in the population and in the market setting over time. And so I cannot really infer much from labels that I acquired maybe even 24 hours ago, because the population I'm encountering in the market right now may exhibit a different trade-off between quality and pay. So I'm going to skip very quickly and show you some results. We experimented with a variety of trade-offs between quality and pay that people reported in the literature. And furthermore, we consider setting where the trade-offs change over time. So we change the trade-offs. So for a bunch of acquisition, there's one trade-off, and then, you know, people from Asia coming online and starting to bid for jobs, and then the trade-off changes, et cetera. We wanted to come up with a policy that's robust. In fact, one of our main objectives was not to come up with a policy that's always superior, but rather to identify a policy that's never the worst one. A policy that is robust is really a policy that we can always count on, that it would never fail. It would never produce sort of miserable results. Some of the results that we started with are, these are not the methods that we developed yet, but sort of non-data-driven methods. For example, some of our benchmarks that we consider is, why don't you always go and pay the highest cost for the labels? Maybe you'll get the higher quality. Sometimes you don't. Sometimes the functions are such that you actually don't get the highest quality, or you pay the minimum amount. So these are kind of non-adaptive, non-data-driven approaches. And what we find about these approaches is that they're not very robust. So sometimes they are the best performance, and sometimes they are really miserable performance. It depends on the market setting. By contrast, something that was kind of robust, that is a non-data-driven, something that doesn't learn, is if you sort of randomly acquire labels at different costs. So you draw a random draw and decide about a certain cost and go acquire it. And this is the blue line. So these are relatively robust. They're never really the worst performance. And this is a situation where the trade-off actually changes. Again, the blue curve is when you randomly change them. So we decided that would be a good benchmark to compare our method with. But as I said before, our method really chooses the cost. It chooses to pay for the cost where the drop in performance, if you remove instances that we previously purchased at that cost, was the greatest, that they've hurt the model the most if they were to remove. And what you see here, this is one of our results. What we evaluated for these plots, for these data sets, is the difference in cost that we incur between the best performance we could achieve with a non-adaptive, with a non-data-driven approach, at what cost we could achieve that same performance with our approach. And we've done this on a lot of different data sets where human labelings are required. And overall, if you can see, the average results that we found was that the savings were between 35 to 36% cost reduction in the acquisition, again, by adaptively figuring out what label cost to ask for. Yes, and so I'll just conclude that this is a problem that we think would be quite useful to study a little bit further in online label markets. We propose an adaptive, data-driven approach. What's good about this approach, other than that it's quite robust, it really doesn't fail miserably ever, at least in our experiments, is that it doesn't really make any assumptions, any limitations on what induction techniques you want to use, you want to learn with. It kind of has a wrapper sort of property that you can wrap it around any learner or any induction algorithms. There are no assumptions about the problem settings or the data properties, et cetera. And it doesn't also make any assumption about the relationship between the costs of acquiring labels and the qualities acquired. And we really explored constant relationship and change in relationships that were introduced in the literature and transitions from one trade-off to another. And this method is really very quite robust. So thank you very much.
Thank you very much. I think we don't have time for questions. Maybe, unless someone has really...
Maytal, I thought that once you are not sure about the quality of the labels, you can just ask several people the same question.
Multiple. So yeah. So repeated labeling is something that's been very popular in the stream of research on online markets. But the difference is that repeated labeling, or the methods that are available, the algorithms that are available for repeated labeling, assumes that the label acquisition, the label costs are fixed. And then you go and acquire more, many of those to decide about the quality of the labels. What we're doing, in fact, can work with repeated labeling, but it addresses a very different problem where you can actually induce a very different quality of labels by offering different costs. And then the question is, how do you dynamically decide what costs to incur? And in fact, we have some new results that work together with repeated labeling as well. Yeah. Sure.